Today we're going to take a look at the multiplication rule of probability. First, let's start off looking at independent events. Now, in the video for independence, we talked about what was the difference between something being independent events and being dependent events. So, if the events are independent, then we can say the intersection of A and B, so the probability of the intersection of A and B, is equal to the probability of A times the probability of B. Now, we're going to look at this in the most basic of terms. So, let's say I have a bag full of marbles. I have 3 red marbles, 2 blue marbles, and 6 green marbles. Now, I'm going to start off using this bag for the majority of my first examples, but let's say we have the probability of choosing a red marble and a blue marble. Now, here's the important thing. We're also told that the first marble is returned to the bag. By having that statement at the end of the problem, that's one of the things that lets us know it is an independent event from the second event. So A is independent from B because it's put back. So we'll call this event A, this event B. So to find the probability of drawing a red marble and also a blue marble, we need to find the probability of red. So notice in this case, we were drawing 2 marbles. The probability of drawing a red marble is 3 out of 11 times, because the intersection of A and B is equal to the probability of A times the probability of B if the events are independent. In this case, we said they were. So 3 out of 11. So the probability of choosing a blue marble would be 2 out of 11. So since these are fractions and I want to multiply, I multiply straight across. 3 times 2 is 6. 11 times 11 is 121. If you put that into Desmos, 6 over 121, you will realize that it doesn't reduce. I'm going to do a similar probability. Let's say we do the probability of drawing a blue and a green marble. And once again, the first marble is put back. Now, once again, this is important. When you look at the example, or when you look at the problems that go along with this, you'll realize that it'll always tell you, or at least the problems that I've set up will tell you, if it's put back or if it's not returned, all right? So once again, this one's put back, so they are independent. So that means I can just do the probability of A times the probability of B. The probability of A times the probability of B. All right, so the probability of drawing a blue marble is 2 out of 11. Probability of drawing a green is 6 out of 11, which when I multiply these, I can multiply straight across. This is 12 over 121. And once again, that does not reduce. All right, so the next example of independence is a situation where we can tell the 2 events are independent. So I'm not using this bag of marbles, I'm gonna use something different. So let's say we wanna find the probability of flipping heads and rolling a 6. So these are 2 independent events, because does flipping a coin have any effect on what number you can roll on a die? No, it doesn't. So flipping a heads is going to be A, rolling a 6 will be my B. So what's the probability of flipping a quarter, have it land on heads? 1/2. What's the probability of rolling a 6? 1 out of 6. So when I multiply my fractions, I multiply straight across, which gives me 1/12. twelfths. So there's 3 examples of when my events are independent. Mowing in the background, brought to you by Green Acres Lawn Care. Now, if I'm trying to find a probability of 2 dependent events happening, then the probability of the second event is directly affected by the probability of first. All right, so if I look at my bag of marbles again, 3 red marbles, 2 blue marbles, and 6 green marbles. Now, the difference is in order to make these dependent events, we're not going to return the first marble. So that directly affects how many marbles are left in the bag. So using this bag of marbles, right, I'm looking for the probability of A and B again, but this time the probability of A times the probability of B given that A happens. Now, I could mathematically find this, but we can also use a little bit of common sense. So using this same bag of marbles, let's say I'm trying to find the probability of a red marble and then also a green marble, and then we're told that the first marble is not returned. All right, so if the first marble is not returned, the probability of the first event A is the probability of my first marble. So it's still 3 out of 11. Now, when we do the probability of a green one, we're basing this on the fact that the first marble drawn is a red marble. So all my green ones are still left in the bag. So it's 6 out of. But if I drew out a red marble and don't put it back, I no longer have 11 marbles. I only have 10. So the denominator is affected because I didn't return one of those marbles. So from here, I can multiply straight across again, which gives me 18 over 110. This fraction simplifies, so I have to make sure I simplify it to 9 over 55. For the next one, still using the bag of marbles, this time we're looking for the probability of a blue marble and the probability of a red marble. So that means, once again, I'm drawing out 2 marbles from the bag, but then we're told the first one is not returned. All right? By not returning a marble, it affects the number of marbles that are left in the bag to choose from. So the probability of event A is 2 out of 10. That's supposed to be an 11. 2 out of 11. All right? The second probability, so the probability of drawing a red marble is 3, because we're assuming that one of these is blue, that this was a blue marble that I took out first. So I still have 3 red ones left in the bag, but now since I didn't put the blue marble back, there's only 10 marbles left in the bag to choose from. When I multiply straight across, that gives me 6 over 110, which simplifies to 3 over 55. So I want to know this probability. I want to know the probability of drawing an ace of diamonds and a red card. Now, when I look at this, it's important to realize that my ace of diamonds is itself a red card. So it's going to affect the number of red cards left in the deck as well as the number of total cards left in the deck. So when I start doing this, we're told it is not returned. So the probability of drawing an ace of diamonds is my probability of A. So the probability of drawing an ace of diamonds is 1 out of 52 cards. All right, there's only 52 cards in the deck. There's only 1 ace of diamonds. Now, the probability of drawing a red card, there are 26 red cards in a deck of cards. But this first one was the ace of diamonds. So the probability of getting ace of diamonds, so that means there is 1 less red card to choose from as well. So instead of being 26, there's only 25 red cards left because we already pulled 1 out. Now, for the total number, there was 52, Now, there is only 51. So once I have these probabilities, I multiply straight across. 1 times 25 is 25. 52 times 51 is 2,652. If I type in the Desmos, hit the little fraction button, I'll realize that this doesn't simplify, so this is my answer. So this is a pretty small probability of drawing the ace of diamonds out of the deck and also drawing a red card.